we're now going to look at the specific proof of inequalities, or algebraic inequalities. Algebraic inequalities, first of all, let's look at properties of inequalities, because we're going to need to know how to manipulate these to do proofs. So the first one, if I know A is greater than B, then A plus or minus X must be greater than B plus or minus X. If I add or subtract the same number, that inequality is preserved. If A is greater than B, then A times X will be greater than B times X, assuming X is a positive number. So you can multiply or divide inequalities by a positive number. Inequality, again, is preserved. However, if you multiply by a negative number, we know the inequality changes. If you change the sign, you change the sign. If A is greater than B, then we're talking about positive numbers here, then the reciprocals, the inequality will change as well. So 1 over A must be less than 1 over B. So inequality sign changes when you take the reciprocal of both sides. Again, we're talking about positive numbers here. If A is greater than B, again, we're talking about positive numbers, then A squared will be greater than B squared. So when you square them, inequality stays the same. If A is greater than B and B is greater than C, then logically A is greater than C. So you can link inequalities together provided the inequality sign is the same. So they were both greater than, so we can link those inequalities together. Alright, again we're talking about positive numbers here. If A is greater than B, greater than 0, and C is greater than D, then A times C must be greater than B times D. So you can multiply inequalities together and preserve the inequality sign. Again, positives, got to be positives we're talking about. And this one then, again, positive numbers, same deal. If A is greater than B and C is greater than D, then we can add the inequalities together and it'll still be true. So A plus C will be greater than B plus D. Alright, so there's some key things that help us with inequalities. Techniques then, how do we approach these problems? This idea gets used a lot because sometimes it's a lot easier to show something's always positive or something's always negative. So we start with the left-hand side, that we move everything across, x minus y, start with that and try to show it's always positive or always negative. So here's a very old question now, but a simple example of that will prove PQ is less than or equal to P squared plus Q squared on 2. So what I will do is I'll start with the algebraic expression where everything's on one side. And so what I want to attempt to do is show this is always negative. Once I can prove that to be true, once I know it's a fact, I can then move terms to the other side and I've got what I want. Alright, well, it's an algebraic fraction question. Let's pull it together and you can see it drops out quite quickly, because on the top we end up with our perfect square, and we know that is always greater than or equal to 0. Therefore, well, I've sort of got the reverse of what they asked, but essentially it's the same thing. Therefore, P squared plus Q squared on 2 must be greater than or equal to PQ. Okay? Remember, you do not treat things you're proving like an equation unless you know it's 100% true. So once I've proven it to be true, then I can manipulate. I can move terms and things like that. Another way of approaching this question, I could have done it this way. I could have, if for some reason you wanted to, you could prove it by contradiction. I could say, well, no, I'm going to assume that actually PQ is greater than P squared plus Q squared on 2. So I'm assuming this to be a fact. So because I'm assuming it's a fact, I'm allowed to manipulate a bit here. Okay, well that means 2PQ is greater than P squared plus Q squared. That would therefore mean eventually that I get 0 is greater than P minus Q squared. But hang on a sec, we know a square is going to be greater than 0. Well, I've contradicted myself. So therefore, what I assumed must have been incorrect. The opposite must be correct then. So PQ, no, I'm not suggesting you would do that by contradiction, but you know, it's another method of proof we now have that we could use if we wanted to. Start with a known result. Start with a fact. If it's a fact, I can manipulate it because I know it to be true. even older, 1994, goodness me. We're going to prove that a squared plus b squared plus c squared is always greater than ab plus bc plus ac. Assuming positive numbers here, by the way. I didn't write it there, but a lot of these you'll see that we assume positive numbers for these inequality questions. Here's the fact I'm starting with. I know a square is greater than 0. A and b are different numbers, of course. So a minus b squared must be greater than 0. Therefore, this must be true. Rearranging that, I get a squared plus b squared is greater than 2ab. But of course, a and b we just simply define to be positive. I could have put any letter there I like, as long as it's positive, it's going to be true. So it must also be true that a squared plus c squared is greater than 2ac. It must also be true that b squared plus c squared is greater than 2bc. I now look at it as 3 simultaneous equations, because remember that rule that said, if we know this is greater than this is we can add them and the inequality is preserved. So therefore, 2a squared plus 2b squared plus 2c squared is greater than, divide everything by 2, we have our result that we're looking for. They then ask this, well hang on a sec, if a plus b plus c is equal to 1, prove that ab plus ac plus bc is in fact less than 1/3. Okay. A squared plus b squared plus c squared is what I'm starting with here. I know the factorisation of that. Okay? It's basically the perfect square rearranged. Another way you could think of it, you remember we did sum and product of the roots? Sum of the roots squared was equal to the sum of the roots individually squared minus twice the sum of the roots 2 at a time. Well, essentially it's exactly the same formula if you think about it. Okay, so we know that to be true. Playing around with that then, a plus b plus c squared minus 2ab plus ac plus bc must be greater than ab plus ac plus bc, because back in part I, we said that a squared plus b squared plus c squared was greater than ab plus ac plus bc. Well, if they're equal, it must also be greater than ab plus ac plus bc. So I now have 3 lots of it. Is less than, moving around the sides there, okay, bingo. Because remember, a plus b plus c is equal to 1. And there we have it. That's less than 1/3. Another idea. Substitute different expressions into known inequalities. Now, if they just tell me it's a positive number, I can put any positive thing in there and it's going to be true. Part C now, to our question from before. Prove 1/3 of a plus b plus c is always greater than or equal to the cube root of a, b, c. Okay, I will start with this result that we proved, that was in part A, I think we proved that one, wasn't it? A squared plus b squared plus c squared is greater than or equal to a. I know this to be true. Now I'm going to use the idea, well, I can manipulate it because I know it to be a fact, so I can move things around and it will still be true. So a squared plus b squared plus c squared minus all that is going to always be positive. I have multiplied both sides, okay. Multiply both sides by a plus b plus c, which of course is a positive number because we've defined a, b and c to be positive, which means the inequality sign does not change. Well, what's the next logical thing to do? Let's just expand the whole thing out. Wow! Let's expand the whole thing out. There it is in all its glory. And you're looking at it and going, wow! I'm looking at it and saying that because my goodness me, there's a lot of cancelling in there. We just have a cubed plus b cubed plus c cubed minus 3abc. We're getting there. So 1/3 of a cubed plus b cubed plus c cubed is greater than or equal to abc. Ooh, that is so close to what we want. Remember now the idea I'm using here. Substitute different expressions into known inequalities. Remember, all I've got to do is substitute a positive number. We said a, b and c are positive numbers. I can substitute any positive thing into a, b and c into that and I know it to be true. So this is what I'm going to substitute in. I'm going to let a be the cube root of a, and I'm going to let b be the cube root of b, and I'm going to let c be the cube root of c. They are positive numbers. So therefore, that must be true. And that is the result we're looking for. Bingo. That brings up this little thing, because what we essentially just proved is the cube run for this idea. Arithmetic mean is always greater than or equal to the geometric mean. We did it for 3 numbers, but it's always true. And you are allowed to quote this. You do not have to prove it, unless, of course, like the last question, it's what you're being asked to prove. Because it would not be a great proof to look at this and go, prove that. Oh yeah, no worries. Arithmetic mean is always greater than geometric mean. Done. No, if that's specifically what you're being asked to prove, then no, you can't. Otherwise, yep, you can just quote that. Hey, part D to this question. Oh, now it gets good. Just suppose, because it could happen, that 1 plus x times 1 plus y times 1 plus z is 8. Now if that's true, prove that x, y, z is always less than or equal to 1. Okay? 1 plus x times 1 plus y times 1 plus z is 8. What's the sensible thing to do? Let's expand the left-hand side out. There it is, expanded. Now I know 1/3 of x plus y plus z is greater than or equal to the cube root of x, y, z. Arithmetic mean is greater than or equal to geometric mean. It also is basically what we just proved in the step before, but it was a, b, c instead of x, y, z. Okay, rewriting that, x plus y plus z is greater than or equal to 3 times the cube root of x, y, z. But really, essentially what this is saying is, anytime you get 3 things, let's just call them things, 3 things, add them together, will always be greater than or equal to 3 times the cube root of those 3 things multiplied together. So my things are going to be x, y, y, z and xz. Those 3 things added together will be greater than or equal to 3 times the cube root of those 3 things multiplied together. So I end up with this. Okay? xy plus yz plus xz. So we've got that in there, we've got that in there. Okay. Now I don't know if you've spotted the pattern yet. Remember, we've got this. So now we know this. Because if that's equal to 8, but I know the left-hand side there is always less than or equal to the line below, because of what we just proved. I don't know if you've spotted it yet, but look at what we got. Maybe if I rewrite it another way. Look at that. xyz is the same as the cube root of xyz cubed. That's a perfect cube on the left-hand side. Well, I can take the cube root of both sides, and the inequality will be preserved. Bingo! There's the answer. Isn't that lovely? I show you that way because I just love that way of doing it. It's probably not the best way of doing it. Okay, now I'll show you the quicker way of doing it, but I just think that's such a great way of doing it. Okay. Again, using the arithmetic mean, geometric mean idea. I know 1 plus x will always be greater than or equal to 2 root x. 2 things added together will always be greater than or equal to 2 times the square root of those 2 things multiplied together. Same is true for 1 plus y, same is true for 1 plus z. Add those 3 things together, I now have 1 plus x times 1 plus y times 1 plus z is greater than or equal to 2 times that, which works out to be 8 root xyz. But hang on, if you recall, they said that that was 8. There's the answer. It's a little bit quicker. Nowhere near as much fun though. Come on. We're going to prove this lovely expression. We're going to trap 2 on a plus b plus 2 on b plus c plus 2 on a plus c in between these 2 expressions. Okay. Well, I'm going to use this idea. And I'm multiplying 2 inequalities together, which I'm allowed to do. The inequality will be preserved. So the 2 inequalities are that a plus b is greater than or equal to 2 root ab, but the other one I've got is 1 on a plus 1 on b will be greater than or equal to 2 times the square root of 1 on a times b. Well, of course, the right-hand side now just turns out to be 4, because they cancel. All right. So what I now have is 1 on a plus 1 on b is greater than or equal to 4 on a plus b. Okay. A and b are just pronumerals. I could use any pronumeral I like. So those 2 must be true as well. Now I can add these 3 things together. The inequality will be preserved. We're dealing with positive numbers here. I now have this. we're getting closer to part of our solution. Let's divide everything by 2, and whilst it's written the other way around, I think we have the right-hand side of our inequality that we want. The left-hand side, maybe not as immediately as obvious, but I'm using the same idea as I did with the last one, but now I'm getting all 3 pronumerals together. So 3 things added together, greater than or equal to 3 times the cube root, and so on. The right-hand side becomes 9. What gave me that idea was the 9. 3 times 3, a new cube, you're going to get me 9. Do the division, and whoa, I just haven't got the middle bit. I've got the right-hand side is greater than the very left-hand side, but does that actually prove that that's in the middle? Because at this stage, that middle could be on the far left-hand side, and it would still be true from what we've proved so far. How do I get that in the middle? Okay. Well, what I'm going to do is this. Remember, I can replace pronumerals with anything I like. Okay, I'm going to replace A with A plus B, B with B plus C, and I'm going to replace C with A plus C. It then becomes this expression. Okay. Well, I think you'll now see we have the other side. I've now trapped it. There is our inequality. A is a positive real number. Show that A on 1 plus A is greater than or equal to 2. Now I claim they are not asking me to prove arithmetic mean, geometric mean here, because that's not how it's set up. It's just proving this. So I can just use it. So, oh well, I know A plus 1 on A is greater than 2. See? 2 things added together, greater than or equal to 2 times the square root. There's our answer. Another way you could do it. Start with a known result. The square root of A minus 1 on the square root of A squared must be greater than or equal to 0. Expand it out, move a term over, whoops, and we got it. That's another way you could do it. Alright, now this one. They're all positives. Show this. B plus C on A plus C plus A on B plus A plus B on C will always be greater than or equal to 6. I got a pretty good idea that I'm going to use this, a number plus its reciprocal. Essentially that's what we proved in part A. A number plus its reciprocal will always be greater than or equal to 2. So let's use it. B over A plus A over B must be greater than or equal to 2. Same is true for C over A, A over C, C over B. Add the 3 together, I now have this. Aha! Add the fractions that have the same denominator, we got our results. Now, let's flip it. You notice this one was, the adding was on the top, the single pronumeral was on the bottom. Let's flip it. A on B plus C plus B on C plus C on A plus B is always greater than or equal to 3 on 2. We just proved this. This is true. Oh, you're not going to like this. Okay, well what I'm going to do, I'm going to replace, why? Why do that? Because that's what my denominators are. I want to get that into the denominators. So I'm going to let A equal the B plus C and so on. But now if I substitute that in everywhere I see A, B and C, look what happens. Ooh, look at the first fraction. I've got a B plus C over a B plus C. Well, that's 1. Look at the second fraction. I've got an A plus C and an A plus C. Well, that's 1. And look at the third one. Yep, there's a 1 there as well. So really, I've got that. Oh, well, let's move the 3 over to the other side. Divide everything by 2. We have our inequality. Let's have a look at a couple of HSC questions that have happened recently. 2021. And they did make the big point though, don't prove it. Using that fact, now my hand is forced, I have to use that. Show that for all non-negative, why didn't you just say positive? I suppose it could be zip, but anyway. A, B, C, this expression is what we're trying to, righto. Well, it said use this fact. This fact was 2 things added together over 2 was that. So all right, I'm looking at, I've got 3 things on top using that fact. Well, I'll just grab 2 of them. It made sense to pick the 2 that are squared. So I said a squared plus b squared on 4, because that's the denominator there. But that means it must be greater than or equal to 2 lots of the square root of a squared b squared on 16. So basically, obviously over 16, 4, put it in half, balances to what we need. Right? And to make it really obvious, what I'm saying here is, well, I did use it. I did, because I could rewrite this to be this, and that's sort of what I used, if you get what I mean. So I might have fudged it a bit there, but I have used it because in my explanation, there it is. So essentially, let's try that again. What I'm saying, I'll go back. This is what I had to do. They told me I had to use this. I don't want to use that. I want to use simply arithmetic mean plus geometric mean. So I've written down arithmetic mean, geometric mean, but damn it, I have to use what they've given me. So in my explanation, I write down what they've given me, and I've said, oh look, I could rearrange this into arithmetic means greater than or equal to geometric mean. I have used what they asked me to use. Thank you. Now, let's play around with it. Okay, so we've got a squared plus b squared on 4 is in fact greater than or equal to ab on 2. Worth pointing out here, when you're setting it out, remember, you're saying this line, the sign you use is how does it relate to the line above. This line is actually equal to the line above, so we write an equal sign, but you then read down. And so long as that inequality is preserved as you go down, you can then in the final statement conclude, well, this is greater than or equal to this. Okay, but we don't have that, we have this. But that is the same as those 2 things added together. Okay, therefore it must be greater than or equal to that, because I know the a squared plus b squared part was greater than or equal to ab on 2. And if we add the same amount to both sides, inequality preserved. So that is okay. Well, once again, we have 2 things added together, and 2 things added together must be greater than or equal to 2 times the square root of 2 things multiplied together. Ah, that's the square root of ABC. Tie it all together. Therefore, we have what they asked for. Now, if you thought that was fun, using part A, but at least they told us you can go another way if you want to. That usually means, when you see that in a test, that usually means don't be stupid. I'm giving you a huge hint. Use part A. If you really want to go do it another way, yeah, okay, go on, go do it. But don't be stupid. This is probably the best way to do it. Show for all non-negative real numbers, non-negative, positive, the square root of ABC is less than or equal to this expression. Okay, well that's what we just proved. Close. All right, well if that's true, that must also be true. And that must also be true. Basically, I'm just changing which of the pronumerals were squared and so on, but it's still just 3 things. I'm just changing which thing I squared and which thing I times by 2. They've got to be true. Add them together, and we get that. Divide everything by 3, and we get that. So it looked horrible, but by geez, it's pretty quick, that one. Last year. This is the one where really, why? It is given for positive numbers, x1, x2, x3, up to xn, with arithmetic mean a. So it's just called the arithmetic mean a, that x1 times x2 times x3 up to xn, divided by a to the power of n is less than or equal to 1. Arithmetic mean is greater than or equal to g. That is what that is saying. Why write it like that? Unbelievable. Suppose that a rectangular prism has dimensions A, B and C and it has a surface area of S. Well, oh yeah, that's it. That's just a confusing way. Why? Okay, show this. ABC will be less than or equal to the surface area divided by 6 to the power of 3 on 2. You probably knew that straight away. You looked at it with it, obvious. There's a rectangular prism. I drew it because I thought that's where I'm going to start. Don't know if it helped me much by having the picture, but it felt good. Nice little picture. I know the surface area will be 2 times AB plus EC plus BC. Okay. Well, AB times AC times BC, using their lovely way they have written theirs, over the arithmetic mean over 3 cubed, because I've got 3 things, would be less than or equal to 1. Thanks for really making this feel difficult. But essentially it's arithmetic mean, geometric mean, but okay, I'm using what they gave. Okay. Well, that's ugly. We don't like fractions on fractions. And a squared, b squared, c squared. Okay, that's what we've ended up with. Well, hang on. That's s on 6 cubed. That's what we have to prove. Oh, we'll find the square root because they're all positives. Take the square root of both sides. Inequality is preserved. Why couldn't we just done geometry? Anyway. But then it said this. Using part I, so inequality we just done, show that when the rectangular prism with surface area S is a cube, it has a maximum volume. You see, if it is a cube, then now A is equal to B, is equal to C. They're the same thing. In other words, ABC is actually A cubed. So we go back to what we just worked out before. S on 6 to the power of 3 on 2. Well, S, our surface area, is now 2 lots of A cubed plus A cubed plus A cubed. So I have, in fact, just got A cubed. That means that when A equals B equals C, the volume, remember, ABC, well, remember the volume is now A cubed. We just said A cubed was S on 6 to the power of 3 on 2. In other words, when it is a cube, this is its volume. But of course, we just proved it's always less than or equal to that amount. So that's the maximum the volume could be. Bingo. When it's a cube, that's a maximum. Done. All right.